Hello class, this is Jared Kamen, Professor of Engineering Technology at Lone Star College Software at the Cypress Center. And what I want to do right now is just to talk about statics condition in which we're using or involving some friction forces. So I'm just going to talk about that, and I'm going to take some notes on that. And hopefully afterwards I'll be able to post some videos as well where we work through some problems involving friction as well. And so one of the most common conditions that you'll see is you'll see an inclined plane and you'll see a box or some type of object sliding down that inclined plane. Alright? So we're going to assume for our purposes that our box weighs 70 pounds. Alright? Let me zoom in a little bit so just make sure you can see that. So we're going to assume for our purposes that our box weighs 70 pounds and our inclined plane is at an angle of 30 degrees. Alright? And so first of all what we need to do is we need to draw a free body diagram of this box and what's happening to it. Okay? So I'm going to go ahead, here we have our box, it's on the slanted surface. So there's the inclined plane there. Alright? We have several different forces acting on this. We have the force of gravity, of course, going straight down, which is its weight, 70 pounds. So we have that. We also have a normal force. So a normal force is a force that a plane inputs onto an object. It can only push, it doesn't pull, okay, and it's when it stops an object from moving. So we have a normal force, and it's always perpendicular to the plane. Okay, so perpendicular means 90 degrees. So our normal force is going to go up this way. We're going to call that force normal right there. Now we have one more force acting, and we're assuming that this plane is not smooth, that it's rough, and so we're going to have a friction force that's going to be opposing the path of motion here. So here's the force of friction right there. Okay. So another thing that you need to consider is that the friction force is always parallel to the surface and opposing the motion. Since we're sliding down this way, our motion is going down this way, and friction is, of course, going the other way. And so this would be our current free body diagram. All right. Now, normally this would be okay, but if you look and see, I'm going to just draw and compare with the horizontal here. If you can look and see here that this is going to be at an angle, of course, of 30 degrees, which is the same as the inclined plane. And this perpendicular is going to be the angle with the horizontal of its supplement. That means it's at 90 degrees minus 30, which is going to be 60 degrees here. Okay? And then 30 degrees here. So you see here we have two slanted forces and one force going in the y direction. And so sometimes you can actually rotate your perspective just to make things a little bit easier, but that way, if we can rotate this a certain way, these two forces, which are perpendicular to each other, won't be slanted anymore, but we're going in the x and y directions, and we'll only have one slanted force, which helps us out because every slanted force we have to break down into rectangular components. So essentially, I'm just going to do this. Okay, it's going to end up like this, where we're on a horizontal plane. Okay. You have your normal force going straight up, your friction force going straight across, okay? And then it's actually our weight is going to be going down at an angle, all right? So let's go ahead and redraw that. So we're going to move this to the side here. We're going to redraw our box, and essentially what we're doing is we're rotating everything counterclockwise 30 degrees, all right? And so when I rotate everything counterclockwise 30 degrees, this plane is horizontal, okay? This 70 pounds, which used to be going straight down, all right, now is going to be off 30 degrees, okay? That's going in the counterclockwise direction. My normal force is going to be going straight up because it's always perpendicular to the surface. There's a normal force here. And then my friction force is always parallel to the surface, so that's going to be going straight across here, all right? And so this would now be my free body diagram, where here would be 70 pounds. And so, excuse me, when I now go ahead and break the slanted force down into rectangular components, I have one component going this way and one component coming down this way. All right? Now be careful because this can be a little bit tricky. So this component here is just going to be the magnitude, which is 70, and then since it's opposite side of our reference angle, it's going to use sine. So we're going to have 70 sine of our angle 30 degrees. Okay? And then this side, since it's adjacent, is going to be the magnitude, which is 70, times the cosine of our angle, which is 30 degrees. Okay? And so now what we've done is we've drawn our free body diagram, we've labeled all of our angles, we've labeled all of our forces, okay? And so this is something that we can work from, all right? So anytime you have a box on an inclined plane, you can rotate it and make sure that you include your normal force, your friction force, as well as your weight. After you rotate it, is going to be slanted, and so you're going to separate that into rectangular components. Now, dealing with friction, you should know that the force of friction is just going to be equal to some constant mu times the normal force, where mu is what's called your friction coefficient or your coefficient of friction. Okay? Throw that in there. So mu is your coefficient of friction, and pretty much what mu is just a constant that helps you determine how these two surfaces that are interacting are rubbing together. Okay. Now your friction force also depends on the normal force, which makes sense because the more force you're pushing up or pushing down on something, the harder it's going to be to move it. So, what if I wanted to determine the frictional force in this particular free body diagram? Okay. So here I need to say I'm trying to find the force of friction. So what is that? Okay, so to do that, what I'm going to do is, remember, assuming that this block is in equilibrium, is I'm going to set up my equilibrium equations. All right. Now I can do my equilibrium equations here in this case by summing up the forces in the x direction. We're going to the right is positive. What force do I have in the x direction? Well, I have negative friction force because it's going to the left, and then I'm going to add this 70 times the sine of 30, okay, and that's supposed to equal 0. And so when we complete this equation, we find simply that the friction force is just going to equal to 70 times the sine of 30, which in this case would be 35 pounds, okay? So that is how I can find the friction force in this situation. Now, what if I also want to find the normal force? Okay. Hey, what is a normal force? Okay. Well, I do the same thing, except I'm going to sum the force in the y direction. So sum of the forces in the y direction, with up being positive, it's going to equal 0. What are our forces in the y direction? Well, I have my normal force, that's Fn. And then I have this component of the weight, which would be 70 cosine of 30. That's going down, so minus 70. Makes that into an actual 70 there. Minus 70 times the cosine of 30. And that's supposed to equal 0. And so now my normal force is just equal to 70 times the cosine of 30, which, if we calculate that, my normal force is going to equal to 60.62 pounds. Okay. Now, what if I'm also interested in finding out the coefficient of friction? Okay. What is mu? So mu is this Greek letter. That's the Greek letter mu, which represents, in our case, the coefficient of friction. And so what we're going to do is we're going to start out with this equation. We know the force of friction and we know the normal force. So that means mu is just going to equal to, let me write that whole equation out first. If I have the force of friction equals mu times the normal force, then divide by the normal force on both sides. Mu is just going to equal to the force of friction divided by the normal force. In other words, our coefficient of friction is just going to equal to the force of friction, which in this case is 35 pounds, divided by our normal force, and our normal force is 60 0.62 pounds. So our mu is just going to equal, in this case, 0.577. All right. So mu is a dimensionless constant, so it has no dimensions. But this is just a way in which you can analyze a block going down a plane. Go ahead, draw your free body diagram, rotate your free body diagram, and then from there you can use your equilibrium equations to go ahead and solve for the normal force as well as the frictional force. And you can do this as long as you have your angle here and as long as you have the weight of the block. Thank you very much.